All right, so yesterday we looked at 10.4, which had to do with lines intersecting. There were three different places they could intersect, either outside the circle, on the circle, inside the circle. And we had ways to calculate the angles based on what situation we had. Well, today we're going to talk about things intersecting again, but we're talking about chords, okay, intersecting inside a circle. Right, so I'll have a picture like this. Here's a chord. Here's another chord. The chords do not have to cross in the middle. Okay, so they don't have to be diameters. Okay, any two chords. Now, you have basically four lengths here. Got 1, 2, 3, 4. If I give you 3 out of 4 of those lengths, you can find the fourth one. Okay, I'm going to show you how. Okay, when you draw two chords, the chords cut each other, not necessarily in half, but they do break the chords into what we call segments. Okay. If I do it in different colors, these are segments of a chord. Okay, so blue, red, green, and black. Those are the 4 segments made when the chords intersect. Okay, so we're going to look at a theorem that has to do with segments of a chord. Okay, what I'm going to do is I'm going to write it out. But I think the most helpful thing would be to look at a picture. Okay, so I will draw a picture of this theorem after. But let me just write it out first. All right, so it starts out with 2 chords intersect in the interior of a circle. Then the product of the lengths of the segments. So we're talking about the lengths of the piece in red, the piece in blue, the piece in green, and the piece in black. Okay, those are the lengths of the segments. So the product of the lengths of the segments of one of the chords is equal to the product of the lengths of the segments of the other chord. Right, so let me draw a picture of that. Okay, so here's your circle. Let's draw 2 chords. Again, don't make it so they're diameters. Just have them kind of off to the side like that. And like that. Okay, let's label them. Let's call that C, B, A, D. And call the point where they cross E. Okay, in that picture, if you take the length of EA times the length of EB, that's going to come out exactly the same as EC times ED. Okay, that's what the theorem says. So you take part of the length of one chord times the other part equals part of the length of that chord times the length of the other chord. Okay, any question on that theorem? Does anyone remember, when do you end up multiplying 2 things together like this on one side, 2 things on the other side, and setting them equal? This is usually the second step of solving a certain kind of problem. Good guess, not an inequality. Think about, when do you cross multiply? When you're solving what? Yeah, a proportion. It's like if you had something like this, you'd do x times 5, okay, something times something, equals 3 times 13. This equation right here is very similar to what we have here. And in fact, the way we prove this theorem involves setting up a proportion and then cross-multiplying. All right? So this is going to be, I think, the only proof we do today. But we are going to prove theorem 10.15. Okay, here's the same picture I just had on the other page. All right. So first thing, you're given that A, B, and C, D are chords. Okay. I marked the point where they cross as point E. And I want to prove EA times EB equals EC times ED. So this times this equals that times that. Oh, what shapes did we use when we did a lot of proofs?
Triangle.
Yeah, we drew triangles. Well, there's two segments I could draw in, right, to make triangles out of those. I'm going to show you what they are. Okay, first thing I'm going to do, I'm going to draw in DB. Okay, and then next I'm going to draw in AC. Okay, so what I just did is I created two triangles. But there's something special about those two triangles.
Are they scaled?
They're what?
Scaled.
What does that mean? If one, what do you mean scaled?
One's bigger than the other, but they're all the same angles.
Yes, these two triangles we just drew are similar. All right. So let's write down what we did. So we're going to draw segment DB and segment AC. Okay. Next, I want to show that I have similar triangles. Okay. Look at angle C and angle B. Angle C is right there. Look at the arc that angle C intercepts. Comes down here, comes down there. That's the arc that angle C intercepts. Is there any other angle that intercepts the same arc?
Yes.
B. So what does that mean about C and B if they intercept the same arc?
The same.
They're the same. Okay.
Didn't we also do alternate interior angles?
No guarantee we have any parallel lines here.
Oh, okay.
Yeah, we don't know that we have parallel lines, but it's a good thought if we did. So next we'll write this kind of as bullets. Angle C and angle B are congruent because they intercept the same arc. Okay. All right. What else do we know?
Same thing about angle A and angle B.
Yep, you could go that way, or you could talk about vertical angles at this point. Either way, we could say angle A and angle D are the same because they both intercept the same arc. Okay, look at D. That's the arc for angle D, what I just drew in green. Look at angle A. This one goes up here. This one goes here. It's the same arc. So now by angle-angle similarity, we have similar triangles. Okay? And that's the whole key. So what did we just say? Angle A and angle D? Because they intercept the same arc. Any questions on that? Okay, so now we're going to write by angle-angle similarity. Triangle AEC. Now you just have to make sure you get the order right. Okay, AEC and DEB. Okay, I'll let you look at it. AEC. Okay, and DEB. So notice I started at the one that was green, went to the middle, and then red. So I'm going green, middle, red. Just keep the order consistent. Okay, and that's the hardest part of the proof, showing that those two triangles are similar. Now, once we know that the triangles are similar, corresponding sides are proportional. Okay, that's what we learned back in the chapter on proportions. Two similar triangles, you can set up a proportion. All right? So let's start with EA. Actually, you know what? Let me write down what I said first. So, because we have similar triangles, corresponding sides are proportional. So when you write corresponding sides, if you pick the second letter and the first letter in one triangle, pick the second letter and the first letter in the other triangle. Just match it up. All right, so we're going to write EA over ED. Okay, it started you off with half the proportion. EA, second first, over ED, second first. Okay, what other side do you think I need to use in the first triangle? It's not EA. Okay, so we used EA. We've got to use it because we want to see it in the final answer. We used ED. What's another side do you think we're going to use from the first triangle? EC. You've got to use EC because it's in the final answer for the proof. If you don't use EC, it won't be in what you want to prove. So we'll do EC. Now, since Luke said second, third, we're locked in. We have to use second, third, EB. But that's fine. That's exactly what we wanted to use. Okay, earlier I asked someone, how do you solve a proportion? What's the name of the thing you do to solve a proportion? Yeah, you cross multiply. Watch what happens. EA times EB equals EC times ED. And that's what we wanted to prove. So EA times EB equals EC times ED. The product of those segment lengths are equal. That's it. That's the proof. Okay, based on similar triangles. All right, so let's use that to figure out the answer for x here. All right, so I'm telling you that ST and PQ are chords, giving you 3 out of 4 of the segment lengths. I'd like you to find the 4th segment length. Anyone think they can set up my equation? What times what equals what times what? Luke?
9x
Yep.
equals 3 times 6.
Good. 9 times x equals 3 times 6. That's it. So you get 9x equals 18. In Denver, what's x? 2. So x is 2. You're done. That's it. Okay, not a hard theorem, just another one of those theorems you've got to try to remember with everything else. All right. I think, personally, the picture that I had on the first page is the most helpful, rather than trying to read through all this stuff. Just look at the picture. Okay, any question on how we got x equals 2? We got a nice answer this time, but it's very possible you get fractions and decimals too. Okay, if you get a decimal, perfectly fine. Don't worry about it. All right. Next thing we're going to do, look at a few new terms. Okay. PQ, or I'm sorry, PR. Look at PR. Okay. PR is a secant segment. Okay, it's a segment because it has a start and a stop. Okay, so it's a segment. And it's a secant because it's intersecting the circle twice. Well, if you look at the part of this secant that's outside the circle, okay, what I colored in red, PQ is called an external secant segment. Okay? Just like QR, you could call that an internal secant segment. It's like a chord, really. And then PS, okay? Well, that's a segment. It's got a start. It's got a stop. And it's only touching the circle one time. That makes it tangent. So PS is called a tangent segment. We're going to look at some theorems with external secants and tangent segments now. Not hard theorems at all, but something that I really think you need a picture for to remember. Okay. Any questions on those two things? What's an external secant and what's a tangent segment? Right. So this is what we pretty much just said. Okay. PS is a tangent segment because it's tangent to the circle right at its endpoint. Okay. If you can look at the picture and see that, you don't need to write that. Segment PR is called a secant segment, and PQ is the external part of the secant segment. Right. I think this diagram sums up everything in words here. You really don't need all that. Okay. That's what's in the book if you want to look at it. So we're going to look at two more theorems. Okay? The theorems are pretty wordy. All right? So I have a picture at the end. I'm going to jump right to the picture. If you really want to copy down all the words, they're all on page 630. I have the words, but I think the picture is a little easier to look at. It's a very simple formula looking at the picture. Okay, in this picture, we have two secant segments. Okay, and they share the same endpoint, point E, outside the circle. And Theorem says that if you take the product of the external secant segment, EA, times the entire length of that segment, which is EB, that's going to be equal to just the product of the external length of the other secant segment times the entire length. Okay, now, we're not going to prove that one. We could prove it, but we're not. Okay. So the length of the external part times the entire length equals the length of the other external part times the entire length. That's the theorem. If you'd like it a little bit more formal, that's what I wrote in words. But that's the picture. Okay, for some people, when they look at it, they get a little confused what's what. It might be helpful if we, if you wanted to color code it. So if you take what's in red times what's in green, that's equal to what's in blue times what's in black. Not sure if that helps you, but. So red times green equals blue times black. Okay. Any question on that theorem? So that's theorem 10.16. Okay. What's different about this theorem? Just look at the picture. Don't read the words yet. What's different about the picture in theorem 10.17? It's very, very similar. Can anyone describe to me what I have here versus the other one? Well, we've got segments, so it might be good to start by describing those segments. Okay. Before we had two secant segments. What do I have now? I've got one what? Yeah?
We now have a tangent as well.
Yeah, I've got one secant segment and one tangent segment. All right? That's the difference. Well, it's almost the same formula. For the secant segment, take the length of the external part, which is EC, and multiply by the entire length, ED. That part's exactly the same as what we did before. Okay, the difference is on the tangent segment. For the tangent segment, you don't have an external part and then an entire length of it. It's the same thing. The entire length of it is the external part. Okay, so the external part of the tangent segment and its entire length are the same thing. So it's almost like using EA twice. It's like writing this. The length of the external part times the entire length equals the length of the external part times the entire length. Right? So if you're going to use EA twice, why not just write EA squared? Really, the same theorem as the one we just did, just a little different. But almost the same thing. So you've got a tangent and a secant segment sharing a common external point. Okay. Does anyone have any other questions on that theorem? Okay, so if I was making the reference sheet, I would just copy down this picture and the formula that's next to it. If you want to copy down the whole theorem, it's also on page 630. But honestly, I don't think there's any value on the test. Copying down all those words won't really help you. Okay. All right, so here's the kind of problem you might see on a test. Find the value for x. Okay, for either theorem, all I try to remember in my head is length of the external part times the whole length equals length of external part times the whole length. If you've got a tangent segment, the external part and the whole length are the same thing. So you use it twice. Anyone think they can set up my equation I'm going to have to solve here? Or maybe just even one side of it. Yep. Okay, careful. Length of the external part, I like that, times the length of the whole thing. Yeah. Length of the external part times the length of the whole thing. 20. Okay, on the other side, Rose, what's the length of the external part? 10. Good. Okay, now yeah, go ahead. 10 plus x. That's the length of the whole thing. Why is it important that I put 10 plus x in parentheses? If I don't, this would be wrong. What am I about to do right on the right-hand side?
Add and together.
Okay, well, those are unlike terms, so there's nothing I can do to add them.
You use the
Distribute, right? If I didn't have those parentheses there, I wouldn't be distributing, and that would be wrong. Okay? Okay, so, oh, and what do I get on the left-hand side?
A 9.
9 times 20?
Yeah. What?
Not 9.
Oh, it's not that 20. Yeah.
Yep.
Oh, you want me to do the problem?
Yeah.
Oh, my bad. 9 times 20 would be 180.
Okay, 180. Distribute out your 10. 10 times 10 is 100. 10 times x is 10x. Okay? So as far as the geometry part of this problem, geometry's done. You used your formula, your theorem, to set up an equation. Now you've got to use your algebra. Okay? To use your distributive property, arithmetic, bring the 100 to the other side. Subtract it. Lastly, divide each side by 10. And what do you get for x? 8. Okay, so the kind of algebra that you have to do is very simple. Okay, don't make a mistake on the algebra part and then get all the hard stuff, like the geometry stuff, right. Okay, I think the geometry stuff that's the hard stuff to remember. Okay, for algebra, you can even use your calculator if you need to.
Mr. Hager,
Okay.
couldn't you just say, like, since the two lines are proportional to each other, like, you took away 1 off the 11, and that makes it 10, and then you take away 1 off the 9, it makes the 8, the x. It'll be the same thing.
We'd have to see if that would always work out that way. Or if that, I'd have to think about it just to make sure that that always works. In this case, it did, but I'm not sure if it would always work. Maybe when we have another example, we'll try it. Let's try another one. Do I have another one? Actually, you know what? I don't think I have another one of these right now, but if we have time, we can come back to that. I can make another one. Or you want to try that right now? You want me to make one?
You know, Mr. Hager, you do you.
Do more time.
You do you.
All right, we're going to go back. We're going to look at a problem we did back in section 10.1. We've already done this question. When we did it before, we used the Pythagorean theorem. Maybe we'll review how we did it that way, but I want to show you guys a different way, okay, to do it now. Okay, in this example, you're standing at point C, which is 8 feet away from a circular silo. Okay, the distance from where you're standing to a point of tangency is 20 feet. They want you to find how big the tank is. All right, so this is the kind of thing you might be, if you were outside, you might have a huge grain silo, and somebody might want to know, well, how big is it? Well, you could take a tape measure and measure the circumference of the whole thing, and if you know the circumference, you could work backwards, use pi to get the radius. Or if you don't have a tape measure big enough to go all the way around, you could just stand at a point, measure how far away you are, measure how far away to a point of tangency, and that'll tell you how big it is. Okay, and there's two ways to do it. Okay, the first way we did it was with the Pythagorean theorem. All right, so to do it that way, okay, I'm going to erase this in a sec, but you draw this in. What shape did we just create?
A
Triangle. Specifically, we know that if you draw a radius to the point of tangency, it's a right angle. All right, so you've got r squared equals, again, this is the way we did it before, not the way we're going to do it now. R squared plus 20 squared. Oops. Okay. One leg squared plus the other leg squared equals the hypotenuse squared. The hypotenuse is r plus how far away you're standing, 8. Okay. This would be the equation you could solve. Okay. And if you did it out, you'd have r squared plus 400. And then this is FOIL, or double distributive. So you get r squared plus 16r plus 64. Look what happens to the r squared. If you have the same thing on both sides, it cancels out. Subtract the 64 from the 400. Okay, you get 336 equals 16r. And your last step was to divide each side by 16. And you get r equals 21. You guys already have this in your notes from section 10.1. Exactly doing it like this. Okay. Now what we're going to do is, let's get rid of that thing I added in. So I'll label this the old way. Now we're going to do the new way. Okay. What we have here really is a tangent segment and a secant segment, and this is the length of the external part of it. So we're gonna try solving it now using the theorem we just learned. Okay, so let's call this the new way. Okay. Anyone think they can set up the equation, what I'm going to multiply to get r?
20 to the second power.
Yep, so you're going to do the length of the external part times the length of the whole thing, which in a tangent segment is the same. 20 times 20. Good. Equals?
8
Yep, 8.
times 8 plus r.
8 plus r, that would get me to right here.
8 plus r squared.
Yes.
No, 8 plus 2r.
Plus 2r, yeah. So length of the external times length of the whole thing. The whole thing is 8 plus 2r. Equals length of the external is 20 times length of the whole thing, 20. It comes out the same. 2r. Okay, do it out. Get 400 equals 8 times 8 is 64 plus 16r. Go back up and just compare what we have right now. 400 equals 64 plus 16r. 400 equals 16r plus 64. We've got the exact same equation, But it was easier because we didn't even have to deal with r squared or the Pythagorean theorem. Okay? A little bit fancier formula, but a lot more, well, I think, simpler algebra, less steps. Okay? Bring the 64 to the other side, just like we did before. 336 equals 16r. And lastly, divide by 16. Okay, so you get the same answer. R equals 21. And was it feet? Yep. Okay, any questions on how we solved it the new way? Okay, when you take the MCAS or you're taking any other test like SATs, things like that, they're usually not going to say you have to solve it a certain way. If you like the Pythagorean theorem, you think that's easier, do it the old way. If you think this external secant segment stuff is easier, do it the new way. Doesn't matter. Get the same answer either way. Okay, this is really very similar to the one we just did. And let's see what we get when we try to do this one. Okay, who can help me set up my equation to find the length of x? So, Olivia, could you start us off? Good. Length of the external part times length of the whole thing. Well, in a tangent segment, they're the same. Equals. And who thinks they can give me what that's equal to on the other side? Selena?
X.
Yep, length of the external part. What? Yep, x plus 4, length of the whole thing. Good. Now watch what happens when we try to solve this. 5 squared is 25. X times x. What's x times x?
2x.
That's x plus x.
X squared.
Yep, x squared. And x times 4? 4x. What kind of equation is that? There's a name for this in Algebra 1, especially because of this exponent. Back, yep. Okay, this is a trinomial, and it's a special trinomial because it has the highest exponent is a 2. Trinomial means there's 3 terms. 1, 2, 3. But when you have a trinomial and the highest, specifically the highest exponent is a 2, it makes it what kind of equation? Not that tough. We've done this in Algebra 1. Quadratic. Very good. This is a quadratic equation. You're not going to be able to get x by itself the way we did in the last problem. Okay? The quadratic term isn't just going to disappear this time. Right? So does anybody remember when you solve a quadratic equation, you like it equal to a certain number? What number do you always want? You can put it on the left or the right. I think it's easier to just put the 25 on the other side this time. Yeah. 0. You want to get it equal to 0. So I'm going to move the 25 to the other side. How would you move the 25? By doing what? Subtracting. Okay, there are no like terms to combine it with. Everything else has an x, 25 doesn't. So you just leave it. Now you've got a quadratic equal to 0. Well, one thing you can try to do is factor it. Okay. In this problem, you could try. You'd start with x and x. But the problem we're going to run into is you need positive middle, negative constant. Okay. That means one has to be positive, one has to be negative. Now you need 2 numbers that multiply to give you 25 and add or subtract to give you 4. Can you do that? No. You can't find 2 numbers that multiply to 25 and add or subtract to give you 4. Okay, not nice numbers. So factoring, I'll even write that down. Factoring will not work. Factoring does not work. Okay. What's another way we could solve that? If you can't factor it, this is a quadratic equation. Anybody remember the other way to solve a quadratic? The quadratic formula. Yep. So we're going to have to use the quadratic formula to solve it. Okay. You could complete the square. Most people don't like that method because they just don't remember it that well and it's a little tricky. So let's write down the quadratic formula. Okay. Does anyone remember what the 3 letters were in the quadratic formula? 3 letters. Like an X, a Y, and a Z. Those aren't the letters, though.
Is there a B?
There's a B. There's a B.
A.
There's an A
C.
and a C. Yeah, there's an A, a B, and a C. Does anybody remember what the quadratic formula is? You know what? Actually, I'll write it this way.
No, it's like, isn't there like square root in it?
There is a square root.
And then
There's something that comes before this. 2 things. Yeah, it's a plus or minus. The first thing you have is a negative b. Plus or minus the square root. Yep, you got a b squared. Anyone remember what comes after that?
minus
There's a minus. And then there's a number, 4. And what are the other 2 letters we have?
A.
A, we already used b.
C.
C. And then it's all divided by 2 times, not C, not B.
A.
Yeah, got to be A. That's the quadratic formula. Okay, I'm not going to spend an entire class going over this in Algebra 1. I would. Okay, you'd spend a whole day learning about it. You just have to know the quadratic formula. Okay, so all we got to do is identify A, B, and C in our equation right there. Okay. Looking at this equation, what's A?
B squared, X squared.
Well, A, B, and C are all going to be numbers. So when we're done, we're going to have all numbers we plug into this. A has a special spot in that formula where it would be. Okay, how about let's go to B. You know, what's B here? Anybody recognize B? No, B's not 1.
0.
B is 4. Okay. Remember, the form of a quadratic is ax squared plus bx plus c. Okay, so when you're solving it, that's the form you want to get it in. That's the form we have it in. All right, so now maybe that'll help us figure it out. So what do you think A is here? 1. Okay, A is 1. What's B?
4.
B is 4. Okay, how about C? Negative 25. Fill in those 4 numbers in those 4 spots and see what you get. Okay, you might have one like this on the test with quadratic formula. Okay, so plug everything in. Negative b. Plus or minus means you're going to get 2 answers. The square root of b squared minus 4 times a times c, all divided by 2a. Now, if you want to do that in your head, you could. I'm going to write it out. Okay, so we got negative 4 plus or minus. What's 4 squared? 16. What's going to happen when you have minus times a minus? Yeah, that's going to be a negative, or minus a negative becomes a positive. Okay, so we got 16 plus, what's 4 times 1? 4. 4 times 25? 100. All over 2. All right, so now we've got negative 4 plus or minus the square root of 116 divided by 2.
4.
This 4?
Yeah.
We multiplied 4 times 1 times 25. Okay, but do not add 4 squared plus 4. You can't do that. Remember PEMDAS, multiplication before addition. So you always multiply these together, then add to the squared number. Okay, let's keep going. You know what? I think we'll round it off because the square root of 116 is not going to come out nice. So let's figure out what that is. 10.77. All right, so our two answers we're going to get, it's negative 4 plus 10.77 divided by 2. Okay, let's do that one first. $3.385. And the other answer is negative 4 minus 10.77 divided by 2. So in theory, there's two answers. Okay, negative 7.385. But now we have to go back up and see what the problem was really about. Because if we were finding the length of something, length should always be what kind of number? What kind of number does length have to be? Positive. So if we were finding length, obviously it's not going to be a negative answer. All right, let's go back up and see what we were actually doing. We were finding the length of something. Okay. It's not that we did anything wrong. It's just when you solve a quadratic, you get two answers. Sometimes you got to pick the one that's appropriate for your problem. In this case, 3.385. Okay. I'll even write down why we crossed it out. Length cannot be negative. So it's 3.385. I think the book rounded it to 3.39. Okay, so not a tough problem if you know your quadratic formula. Okay? I think the geometry part here was easy in this case. This equation, super simple to set up. Solving it, well, that gets into a little bit more advanced algebra 1. Not too advanced, but a little bit advanced. Okay, any other questions on that? All right, so really today you guys learned three different theorems. You got the one about the secants that cross inside the circle, and then you got the one where you got a secant and a tangent that meet, or two secants that meet. Okay. And those are really the last three theorems that we're going to be learning about circles. Okay, tomorrow will be mostly drawing and sketching circles. Okay, so if you have some graph paper, that might be handy. If you've got a compass, you could bring that. Otherwise, I've got a compass you can borrow. All right, so the homework's on 632. 2 through 9, I'd like you to try all. 13 to 27, just the odds. 30 and 31.